Hello, my name is Austin Burba, and for my second midterm, I was assigned paper number 8, Alumina Lattices Compressed. You can see pictured to the left the 5 different lattice compounds that were tested in this paper, all 5 of them. The title of my paper was Compression Performances and Damage Mechanisms of Aluminum Oxide Ceramic Lattices Fabricated by Additive Manufacturing, Imitating Metal Crystal Structures. You can see all of the authors listed here. This comes out of the Ceramics International Journal, Volume 49, year 2023, pages 1,419 through 1,435. The scope of this paper was replicating metal crystal structures in ceramics for increased compressive strength. Like I said earlier, there's 5 of these different lattice formations, each one inspired by metal crystal structures that we've all seen in the past. And one of the key questions that the article looked into was which lattice structure tested is going to be the most resistant to compressive stress. Next, I'm going to go over the methodology. There was 5 different models used, the first being the SFCC compound, the FCC, the SC, the BCC, and the HCP lattice formations. They were all tested in cube-like formations. You can see pictured to the right. And like I said earlier, they all are inspired by metal crystal structures. There's 3 different ways that these materials performances were tested. The first one being through a physical compressive test. This was done by putting a load in the middle of the printed structure, seeing where failure occurs and what the stress strain curve kind of looks like for the material. The next one was through numerical solutions in a newly acquired software called ABAQUS. This helped do numerical solutions rather than actually having to print off the material and test it. And lastly, of course, there's traditional static structural FEA tests. These were vigorously ran on each lattice type. And the materials that were surveyed is of course, the aluminum oxide ceramics, the things that we're looking into, seeing what we can optimize and what it was compared to, which is the general metal crystal structures that we've all come to know. Next, I'm going to go over the first key result from the study. This answered the question, which lattice structure comes with the greatest compressive strength? So you can see pictured here every single lattice structure's stress strain curve for a compressive kind of scenario. The compression stress strain curves are shown for the X, Y, and Z directions. And there's also, for the pink graphs, solid bars showing centering temperatures of 1,650 degrees Celsius, dotted lines showing centering temperatures from 1,400 degrees Celsius. And for the green graphs, the solid line shows a strut diameter of 1.1 millimeters. The dotted lines is a strut diameter of 0.7 millimeters. Looking at these stress strain graphs, it becomes apparent that graph D, which correlates with the FFCC lattice, has the greatest compressive strength for each compressive scenario. This shows that this formation is the greatest compressive strength wise out of the 5 that are tested. We can also get out of this data that a greater centering temperature and a greater strut diameter has a very large impact on the compressive strength of the materials. The next thing I want to go over is the second key result from the study, and this is answering the question, what are the different failure methods for the lattice structures? As you can see here, the physical test that I was mentioning earlier is shown. It's a just force down in the middle of the cube. And even though this force is the same, there's various different failure theories that we see. The first being B, the layer collapse, you can see pictured here, or various different parabola types of collapse, one being a symmetrical one, pictured in part C, D being one that offsets to one side, and E being another symmetrical one. We see in F a tilt collapse, and in G a total part collapse. You can see pictured in the graph in H that in spite of SFCC seeing the largest compressive strength, it also sees a high displacement in its loading phase. So maybe this is something to look into in the future, see how this displacement will affect its performance in the real world. In summary, metal crystal structures work in other materials such as ceramics. We took the article takes the 5 different formations saw in the metal crystals, applied to ceramics, and saw positive results. Secondly, SFCC lattice structure was the most beneficial. It had very high compressive strength compared to general ceramics, and it also compared to the other lattice structures. Next, failure theories are dependent upon print quality, nodes, and struts. You can orient and change where the nodes and struts are and what angles they see to affect the different types of failures that occur. And lastly, the only critique I have on the paper was that there was a lack of running each study with different materials. The paper only does it on aluminum oxide. I think it would be very interesting to see what this does, these lattice formations do for different materials. And of course, a lack of cost analysis associated with the lattice structures. I would like to see how traditional 3D printing with ceramics cost-wise compares to the lattice structures. That's all I have. Thank you.